AP Chemisters, this is Mrs. Vanderlei bringing you Blankwalle Chapter 6, Section 9. This is determining enthalpies, remember that's delta H, of a reaction from standard enthalpies of formation. So let's kind of go back and see what we've done so far. We have found enthalpy a couple ways already. Experimentally, and that's where like Q equals MC delta T. And enthalpy, if you need to write this down, go for it. And delta H at constant pressure is your Q value. So that's why we can use a coffee cup calorimeter and say that the Q value we found is really your delta H, but watch your units. How else can we find delta H of a reaction? We can use Hess's law. And guess what? There's another way, and we can look up using standard enthalpies of formation. You remember that those charts that I had given you at the beginning of this chapter that has all these this data on it. If you can pause this and find that, get it out, and come back. Okie dokies, I hope you have it. So delta H again means a change in enthalpy or a final enthalpy minus initial. Remember, delta anything is final minus initial. So we're actually going to use that idea in this section, okay? And it says H is not an absolute value. We can assign a zero value in standard values. So it's all relative to one another. It's kind of like how they came up with the atomic mass. They made, 1/12 of carbon 12 to be equal to 1, and so everything else is relative off of that. So anyway, we can do the same thing with delta H's. We can assign a value being 0, and everything relative to it will be given a number, okay? So let's see what we mean by this, standard values. What is a standard value? Okay, so a standard state is a precisely defined reference state for a compound. If it's a gaseous state, the pressure of 1 atm, pure liquid or solid, the standard state is that pure liquid or solid, and a substance in concentration has a 1 molar solution. Standard enthalpy change is a change in enthalpy where all reactants and products are in their standard states, shown by the degree symbol, that delta H with the naught or the degree. And so when we go back and look at some of these things, like even for elements, okay, what is the standard state for an element? Well, it depends on what it is. If it is hydrogen gas, it would be a gas, not a liquid or a solid. If it is, let's say, mercury, it will be a liquid. If it is iron, it'll be a solid. If it's anything else besides that, it's not in its standard states, okay? All right. So the standard enthalpy change is a change in enthalpy where all the reactants and products are in standard states, and it's shown by that H naught. All right, so let's see how we do this. Standard enthalpy of formation is the delta F. That F is really important because it tells you this is where we're getting this information from this chart. So from a pure compound, the change, this is important. I would star this or highlight this or something. A standard enthalpy of formation for a pure compound is a change in enthalpy when 1 mole of compound forms from its constituent elements in their standard state. Don't worry, we'll practice this, but that's a great definition. Pure element, the delta H formation naught, the standard state is 0. Let's look down here. Look at everything, oops, that is an element on this chart. Here is bromine gas. No, that's not an element. That's not a standard state, but bromine liquid is, look at 0. Calcium solid, 0. Carbon graphite, 0. Chlorine gas, 0. Do you see all these? So they're elements in their standard states. The heat of formation is 0, okay? So if I were to look at this particular example where the carbon solid, graphite, plus 2 hydrogen gases yields methane gas, we say the heat of formation is negative 74.6 kilojoules per mole. Per mole of what? Per mole of methane. So if we look down here, is methane given as anything? Here it is, negative 74.6. And that's where these numbers came from. So if I were to burn 1 mole of graphite with 2 moles of hydrogen gas and I get 1 mole of graphite, how much energy is released? Well, it's a negative. How much energy is released by doing this? Negative 74.6 kilojoules per mole. Okay, so you can measure that. You can use a calorimeter, you can use Hess's law, whatever. But if you measured that, that's what that methane is. It is from its constituent elements in their standard state. So carbon, where it's a 0, well, what's 0 carbon? That's your graphite. That's this. The hydrogen is its standard state, and those elements make up the methane. Okay, so we're going to practice this on the next page. Okay, so problem number 44. Are these its standard reactions? Okay, so the first thing you're looking at is, am I creating 1 mole of product? Yes, I am. That's good. So what elements make up sodium oxide? Well, sodium and oxygen. So how do I make sodium over here? So it's a solid. I need 2 moles of it. And I need oxygen. I need only 1 mole of oxygen, so I have to have a 1/2 here. So I have a total of half times 2 is 1, and gas is its standard state. So yes, letter A is indeed in its standard state. So what about letter B? Do we have a little problem here? We have a lot of problems in letter B. Holy cow. All right, so what's one thing that you see? Well, what's wrong? How many moles of product do I need? 1. How many are in letter B? 2. That's wrong. Look at its reactants. I need potassium, but what's the standard state of potassium? It's not liquid. Holy cow. Oh, I need 2 chlorines. Well, sort of. For the way they wrote it, I need 2 chlorines. But what's the standard state of chlorine? It's not a solid, it's a gas. So we have some real problems with letter B, all right. So it is not. Why? Because you can only have 1 mole of product formed. I have 2. Potassium and chlorine are not in their standard states. So why don't you jot down letter B and fix it? So make letter B a standard reaction. Go ahead and do that. All right, let's see how we do this. Well, this is what I came up with. So I needed, first I'm going to work over here. I only need 1 mole of KCl. Oh, I should put a little solid underneath that. I apologize. So I need 1 mole of KCl. So what do I do to get potassium chloride? I need some potassium. So what is potassium in its standard state? Solid. So that's where this came from. And I need 1 chlorine. Well, what's chlorine in its standard state? It's diatomic and it's a gas. So that's why I need a 1/2 of that. And so potassium solid is in its standard state, chlorine gas is in its standard state, and now potassium chloride is in its standard state, and I have 1 mole of this. Okay. What about letter C? What do you think about that? Is it in a standard reaction? Yes or no? Well, I'm hoping you said no, and again, for several reasons. All right, it is not. Well, number 1, if you can read that, sucrose is not being formed, it's being decomposed, okay? So it should be flipped. So you should have 1 mole of, actually it's not sucrose, it's glucose. So we should have 1 mole of glucose being formed, not being a reactant, okay? And the other one is, if you look closely, diamond is not the standard state of carbon. Graphite is. So if I wanted to fix this, I would move this over here and put these things over on the other side, and I'd make this a graphite and not diamond. Okay, I believe some of your bookwork problems will have you be doing the same thing. Okay, let's look at problem number 45. Well, I guess not only does your bookwork have you do some of the stuff, but we're going to practice that right now. So write equations for the formation of each of the following for the respective elements in their standard states. Include the delta H of formation, not for each. All right, so what do I need to make magnesium carbonate? I need some pure magnesium, some carbon, and some oxygen. So what is magnesium in its standard state? Solid. What's carbon in its standard state? Solid graphite. What's oxygen in its standard state is O2, gas. Okay, so what do you have to multiply the coefficient of oxygen for that to work? Well, I multiplied it by 3/2, so I have a total of 3 carbons. So what else now? I had to go look up online. This is not in your chart, so I looked on the internet and found the heat of formation to be negative 1095.8 kilojoules per mole. Notice a couple things. Why do I have this not there? Well, it's because magnesium and carbon and oxygen and magnesium carbonate are all in their standard states. Okay, so that's important. Why do I have the little F here? Because I wrote it as a heat of formation. meaning I have them coming from their elements, making their that compound. Okay, why don't you do C6H12O6? So pause this, do it, and come back. All right, welcome back. Hopefully you got it. So, oops, this is what I got. Hopefully you got the same thing. And what's the delta H of formation? Did you look that up? If not, go look it up. Okay, this is what I got. Delta F, and that is in that sheet that I provided you, so you can see it right here. F of naught is negative 1273.3 kilojoules per mole. So again, why is there a naught? Because all four items are in their standard state. Why is it a formation? Because you have this compound being made from its elements, okay? So somehow write that down, commit this to memory, what each of those little things mean, okay? Let's look at Roman numeral 3. Hey, we're back. So anyway, part 3 says, or this next part says, recall, a chemical reaction involves two steps, breaking bonds and bonds forming. So I just want to use an example of maybe take sucrose, this is indeed sucrose, and burn it. And so what is always the first step? I always have to do what? I have to break bonds, okay? So what does that involve? Bonds breaking are your reactants, and your original compounds are becoming their elements, okay? Look what I just said. The original compounds like C12H22O11 is becoming their elements. So I need to start here, and I'm going to break some bonds. And what do I make up here? I'm making the elements of carbons and hydrogens and oxygens. So aren't I doing the opposite of my heat of formation? Yes, because what does that mean? A heat of formation is where I take the elements and make the compound. Well, when I start off any reaction, I'm going to break bonds, and that's the opposite of what heat of formation is. So that's why it's a negative heat of formation. That's why it's the opposite, because I'm doing the opposite thing. I'm switching around. And remember when we started Hess's law, if you reverse it, the delta H gets the opposite sign, doesn't it? So what's my next step? I'm going to make some new bonds, aren't I? So what happens here? All right, I'm making new bonds. And so what am I making? Well, I know I'm going to make carbon dioxide and water. Here, I'll put this over here, carbon dioxide and water. Okay, so bonds are forming, and so I'm going from these elements to the compounds, all right, which is heat of formation normal. I'm not going to have to change the sign. So once again, I want to show you this, that when I'm breaking bonds, it's endothermic always. And when I'm forming bonds down here, it's always exothermic. So that's why here I'm going up, right? So this is going up, I'm absorbing energy, and here I'm going down, I'm releasing energy. Okay, so kind of make sure you have that in your mind too. But as we go, so if I want reactants to become products, I'm going to add these two things together. So if I add F1 and F2 together, all right, reaction 1, reaction 2, this is what I have here. Keep this in mind. This is my beginning reactants, and this is my products. Now, normally we don't like seeing a negative sign first and a positive sign next. So what if we were to flip this? All right, then it's the products minus reactants, all right? And this is the equation that you're going to want to use. If you find, your equation sheet, that yellow one I have given you, this is in your equation sheet. You don't have to have it memorized. It's in your equation sheet. So let's go to the next page. Alrighty, Rose. So we're going to do a similar thing. We're going to put numbers to it. So let's burn some methane with oxygen and make carbon dioxide and water. Okay, so here is exactly what's happening. We're starting off here with our reactants, and I'm going to decompose methane into its elements. Okay, so I have the carbon, graphite, and H2 right here. And I need to absorb 74.6 kilojoules of energy. You might recognize this as the value that we had before, but we had a negative 74.6. Here, let me show you this. Let's go back a couple pages. So here we go. Does this look familiar to you? All right, here we have carbon plus hydrogen making methane at a negative 74.6 kilojoules per mole. Well, look at the opposite, has methane becoming carbon plus hydrogen, and that's a positive 74.6. Let's go on to the next, or that same problem again. All right, so we're back to here again. So here's our methane becoming carbon plus water, or plus hydrogen. And notice my oxygen. I didn't really do anything with oxygen. It's already an element. I don't need to break it down any further. And besides, isn't the heat of formation of an element 0? So I don't really have to worry about that. So now that I have its elements, I'm going to form it into carbon dioxide, which is a negative 393.5, and I'm going to make 2 waters. Okay, so if I add these 2 parts together, then I get my final product. So it says, what's the delta H reaction for this? All right, oops, sorry. Let's check this out. So here the reaction is here the bond's broken, plus here the bond's formed. So my bond's broken is plus 74.6, plus my bond's formed is negative 395 or 3.5 and negative 483.6. That's what this number is right here. So I have a negative 802.5. By the way, I want to show you something. Where did this number come from? Will you go to the prior page? Let's look at this chart real closely. Remember carbon dioxide? Oh, look at that. That's that 393.5. Let's find water now. Do you see where water is? It's over here. All right, that negative 480 something, right? That's right here, isn't it? All right, but it isn't. It's negative 241. I thought it was something big, like negative 485. It is, all right, or 483, I guess. Where did that negative 483 come from? I doubled this value. Why do you think I doubled this value? Because I have 2 moles of hydrogen gas formed. So I took that heat of formation, that negative 241.8, and I doubled it at negative 248, or excuse me, negative 483.6. All right, and so that's how I got that value. That's where this number came from. Notice I added those 2. Remember I said and carbon dioxide and the water? Notice I added those 2. I notice I'm well over my 15-minute mark, so why don't I stop here and I will stop it so we'll have another video too. And I always stop with, don't wait to be great. See you later, next time, soon, bye.